In this video, we're going to be differentiating from first principles. That means using this formula to find the derivative of a function. We derived this formula in a previous video, so if you want to understand where this formula comes from, what each part of it means, and what differentiation is, then check that video out. There should be a pop-up in the top right-hand corner. So let's go ahead and have a look at the first example. It says, prove from first principles that the derivative of x cubed is 3x squared. So we're going to say that f of x equals x cubed to start off with, and then we're also going to write down the definition of the derivative. So always, I think, when you're starting these problems off, write this down because it helps to remember it, and it's good practice to start your problems off by writing down the formulas that you're going to be using. Okay, so now when we look at each part of this formula, we've got f of x plus h. That input is now x plus h, so we want to plug that into f of x and plug that into the formula. So we've got the limit as h approaches 0 of f of x plus h, so we're going to have x plus h cubed. Take f of x, which is just x cubed, all over h. And then we want to expand these brackets out. So here you might want to think back to the binomial theorem if you want to take a bit of a shortcut. That says if we expand this out, we're going to get x cubed plus 3x squared h plus 3x h squared plus h cubed. Take x cubed all over h. And then let's see what we can simplify. So we've got a positive x cubed and a negative x cubed. They're going to cancel. Then on the top line, let's factorize out an h from each term. So we're going to have the limit as h approaches 0. Always remember to include that. We're going to have h multiplied by 3x squared plus 3xh plus h squared all over h. Then we can cancel those h's, and we are left with the expression in the brackets. So this is going to be the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Okay, so now think back to what the derivative is. That involves evaluating what's happening at the limit. So we want to now ask the question, what's going to happen to this function as h approaches 0? So you look at each term. Well, what's going to happen to 3xh as h approaches 0? That's also going to approach 0. They are directly proportional. So we say as h approaches 0, 3xh approaches 0. What about h squared? That is also going to approach 0. So then we can say the derivative f dash x is equal to 3x squared, which was what we were asked to show. So that was the first example. So I want to just give a brief example of what this means again, in case you've forgotten from that first video. So an example of what the derivative is the gradient of the function. So if we think about x cubed in terms of its graph, so let's draw a quick graph here. It doesn't have to be perfect. So let's say x cubed looks something like that. It has the triple 0 at 0, 0. The derivative f dash of x is the function of the gradient. So let's say we wanted the gradient of the curve at this point here, whatever that is. F dash x, or the derivative, is giving us the gradient of the tangent at that point, or the gradient of the curve at that one point. Okay, so if this point was, for example, at x equals 3, this being the x-axis, of course, then we could say that the gradient at that point would be plugging 3 into 3x squared. So 3 times 9 would be 27. So clearly my diagram isn't very accurate, but that's the idea of what the derivative is in terms of the graph of the function. There are other interpretations of what the derivative is, but at this point, that is our main interpretation of what it is. Okay, so let's have a look at a few more examples. The next one was a quick one. What is the derivative of a constant like 2? The point of this is to understand Well, when we derive a constant, what are we always going to get? So let's let f of x equal 2, and then let's write our definition of the derivative out again. So what is f of x plus h going to be when f of x equals 2? Well, there's no input, there's no x, right? So f of x plus h and f of x plus 10,000, all of them are just going to be 2. So f dash of x here is going to be the limit as h approaches 0 of 2 take 2 over h, which is just 0. So we can just say f of x equals 0. We don't even need to consider the limit there. If you want an intuitive understanding of what this means, well, what does it mean when f of x equals 2? That means we have a horizontal line at 2 at y equals 2. So something like this. This would be y equals 2. And then, so every point on that line is at 2. And then what's the gradient of this line at every point? It's 0, right? A horizontal line has a gradient of 0. So wherever you go on that line, f dash of x, or the derivative, will be 0. Okay, so that was a quick example of what we do with constants. Let's have a look at another one. Example 2, well, I should say example 3, but this says, given that f of x equals 3x squared, take 5x, use the definition of the derivative to find f dash of x. When it says definition of the derivative, this is another way of saying from first principles. So again, this is indicating you need to use that formula. So let's write it out. F dash of x equals the limit as h approaches 0. And hopefully you know what's coming next. F of x plus h take f of x over h. Okay, let's plug x plus h into the function. Always remembering to write your limit. So x plus h into this function will give us 3 times x plus h all squared. Take 5 times x plus h. Take f of x, which is 3x squared, take 5x. And this is all over h. And I forgot to say at the start, keep your eyes peeled for some patterns as we take these derivatives. So here we're deriving 3x squared take 5x. See if you can notice something in relation to the exponents and the coefficients. So remember that the derivative of x cubed was 3x squared. Do you see a relationship between the coefficient and the exponent? And maybe form a hypothesis about what is happening with the power of x, and then what's happening after we take the derivative. And so maybe form a hypothesis now and then test that as we go through the examples and see if you find evidence to support that. So let's continue with this example. So we're going to expand all of the brackets. So this is going to be 3 times x squared plus 2xh plus h squared. Take 5x, take 5h. Take 3x squared plus 5x all over h. Okay, let's see what we can cancel. So we have a negative 5x and a positive 5x. We're going to have a 3x squared here and a negative 3x squared. So what are we left with? Let's see. So the limit as h approaches 0 of 6xh plus 3h squared take 5h. So I already distributed that negative to both terms there. All over h, and then we can cancel that h with the h's in the numerator. So we end up with the limit as h approaches 0 of 6x plus, let's write it like this actually, 6x take 5 plus 3h. And now we evaluate what's happening at the limit as h approaches 0. So as h approaches 0, what's happening? Well, 3h is going to approach 0 also. So then for the derivative, we're going to be left with 6x take 5. Okay, so the reason I asked you to look for patterns here is because using this formula is actually quite clunky. We don't actually want to keep using this formula every time. We want to start looking for shortcuts. It's kind of like, I'll compare it to the index laws. You know, you understand that x squared times x to the 3 is x times x times x times x times x 5 times. But we don't write this out every time. We just say, well, a shortcut is to add the exponents. 2 plus 3 is 5. So we don't always have to do everything from first principles. I also should have talked about what that means from first principles. That means from basically without taking anything for granted, we're going to prove everything from the bottom up. We don't need to do that every single time. We can take shortcuts. So that's what we're looking out for here as we use this formula to take these derivatives. We're looking to see if in the future we can do it in a bit more efficient way. So let's have a look at one more example. So have you formed a hypothesis about what we're doing with the exponents yet? See if it still holds up for this example. This one says, prove from first principles that the derivative of 1 over x is negative 1 over x squared. So here we're going to let f of x equal 1 over x, or you can also write it as x to the negative 1. Okay, so let's again write our formula out. Okay, what's going to happen when we plug x plus h into this function? Well, I'm just going to initially write it as x plus h to the power of negative 1. Then we're going to subtract f of x, which is x to the power of negative 1, all over h. And now I'm going to write this slightly differently. Slightly differently. So I'm going to factorize the 1 over h out. And now I'm going to write this as 1 over x plus h, subtract 1 over x. So this is the same thing, just written it slightly differently. Okay, now I have two algebraic fractions. I want to combine those. So the common denominator is x times x plus h. So I need to multiply the first fraction by x. So this becomes x times 1, which is just x, and then the second fraction by x plus h. And this is all over x times x plus h. Okay, actually I should remember to put brackets around the x plus h because that negative will be distributed to both of those terms. So let's see if we can do some simplifying now. In the numerator we have x take x, they're going to cancel, and then we're left with the negative h. So let's write this as negative h over x squared plus xh, expanding those brackets. And then we can cancel the 1 on h that's multiplied by this whole thing by the h in the numerator. And then we're left with the limit as h approaches 0 of negative 1 over x squared plus xh. And so now we evaluate what's happening at the limit as h approaches 0. What's going to happen here? Well, x plus h is going to approach 0. So then we're left with the derivative equal to negative 1 on x squared. Okay, so now I'm going to draw up a little bit of a table with the derivatives we've found so far, and hopefully we can notice a pattern here. So first we started with x cubed. The derivative of that was 3x squared. Then we did 3x squared take 5x. The derivative of this was 6x take 5. Then we did x to the negative 1, and another way of writing this is x to the negative 2, or negative x to the negative 2. So that was the derivative there. So can you notice what's going on here with each function? So what I hope you see is that when we have an exponent, say, of 3, we are then multiplying the coefficient by 3. When we have an exponent of 2, we are multiplying the coefficient by 2. When we have an exponent of negative 1, we multiply the coefficient by negative 1. Also, the exponent is decreasing by 1 each time. So if we have negative 5x, the exponent of x is 1, then the exponent becomes 0. X to the 0 is just 1. Or 3x squared becomes 6x, the exponent of x is now 1. Okay, so that is actually a rule we can use, and we're going to derive this here. So this is the last example we're going through. It says use the definition of the derivative to find f dash x given that f of x equals ax to the n. And I'm going to do this for n being a natural number, although this rule extends to any real number. So n could be a fraction or a negative number, and I'll explain why at the end. Okay, so let's write down our definition. So again, the limit as h approaches 0 of all of this. Okay, let's plug x plus h into our function ax to the n. So what happens with that? Well, we're going to have a times x plus h to the n. Take ax to the n all over h. And now we really need to understand the binomial theorem to understand what to do with this x plus h to the n. So think back how we expand those brackets with a natural number exponent. We learnt about that when we looked at the binomial theorem. So this is going to be, well, the first term, the coefficient is n choose 0, the exponent choose 0, x to the n. The next term is n choose 1, x to the n take 1h. Then the next term is n choose 2, x to the n take 2h squared, and so on all the way up to n choose n h to the n. Okay, and then we have the take ax to the n on the end. Okay, so now what's going to happen? All of that is multiplied by a, actually, so let's do some squared brackets there. All right. Okay, so this first term is just going to be x to the n. So basically what we're going to find is that everything's going to cancel out or disappear as h approaches 0. But let's evaluate these first few terms. So n choose 0 is 1, so that first term is just x to the n. N choose 1 is n. So the second term is n x to the power of n take 1h. The third term in that expansion, well, let's just leave it as is, and so on. And then we subtract ax to the n all over h. Okay, so the point is here that the ax to the n always cancels with the function you subtract in the numerator. So f of x take f of x is always 0. And then when you cancel with the h in the denominator, we're always left with n x to the n take 1 in the numerator. And the rest of the terms have an h in them. So if we look at what's happening in the numerator here, we're left with n x to the n take 1. And let's not forget this is multiplied by a. Then the next term will be n choose 2, x to the n take 2 h. So the h in the denominator cancels with one of the h's in that term. Then the next term would be n choose 3, x to the n take 3 h squared, and so on. And the important point here is that all of these terms will have h's in them. So as h approaches 0, these terms will also approach 0. So e.g. n choose 2, x to the n take 2, h approaches 0. So we get for the limit or the derivative a and x to the n take 1. Okay, so this is the rule we're going to be using, and that was a derivation for the natural numbers, but this would also work for any real number because these terms, even though the coefficients would be slightly different, the only one we care about, which is n choose 1, would still be the same. It would just be n, or whatever real number you used for n. So this still works whether n is a natural number or a fraction or a negative number. We can still use this rule. So this is where we're going to start in the next video with this rule, and hopefully find some other shortcuts as well. So it basically says if f of x equals ax to the power n, then f dash of x, the derivative, will be n a x to the power of n take 1. Okay, so this is what we're going to be doing when we have a function of this form. Rather than always using that formula from first principles, we're looking to do to use this rule and other rules like it, which we'll explore further. Okay, I hope you found this video useful. Please leave a like if you did, subscribe if you want to see more content, and I'll see you in the next one. Bye for now.